Welcome to Almost Here, Round the Corner Future Technology podcast with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hello, this is Richard Jacobs with the Future Tech podcast. My guest is Girish Chowdhary. He's an assistant professor in the Agricultural and Biological Engineering Department at the University of Illinois. Girish, how are you doing today?
I'm doing great. How are you, Rich?
Good. Yeah, so tell me, I see in my notes you work in the Intelligent Robotics Laboratory. So what kind of work are you doing there?
So I work in the area of field robotics, which is essentially robots that operate in outdoor environments trying to do difficult things.
Okay. So what are some examples? Outdoor, like in a mine under the earth, or outdoor just in a field,
Right. Yeah. So,
farming.
farming is basically the main area where I'm focusing on right now. But in the past, I've focused on defense type applications and autonomy type applications. But currently, I'm focusing on agricultural robotics. So in that case, the robots would be operating in outdoor environments that are unstructured, changing, and uncertain.
Yeah, when I think of agricultural robotics, I think of just like a gigantic combine, going through a field and, pulling in plants and chopping them up. Are the robots you're working on those kind, or are they different, smaller ones that do different tasks?
Right. Yeah, that's very true. The current way the agricultural equipment is designed is to be very large and powerful, and basically to reduce or enable one person to take care of large areas in a sufficiently short amount of time. So we are trying to develop a different kind of robotic system that does not necessarily require power or size as a key benefit, but instead several small robots can work together to accomplish tasks in field environments. So they are very different from the traditional large robots.
So what kind of agriculture would they be used in? Any of the kinds that we see, like harvesting gigantic fields of corn, or are there specific types of plants that this would be used on, or would it be used in, groves where there's trees of stuff?
So what we're working on are teams of robots that are autonomous and intelligent, but by themselves, they're not very expensive or big. And the idea is that starting from simple tasks such as monitoring and measuring, these robots could do more and more complex tasks over time. So to begin with, right now, we're working on robots that go through plots and try to measure plants. This is called as phenotyping. And phenotyping is one of the key things that is necessary to breed better seeds. So you may know that corn, for example, or maize never existed in nature, right? So around now 9,000 years ago, our ancestors started breeding a plant called teosinte with other plants, and over time, this new variety called maize was discovered. But right now, there's a need to accelerate that breeding so that we can feed the globe. And one way of doing that is to characterize the environment in which the plant exists and try to figure out which genes in the genome of the plant are responsible for the traits that you would like the plant to exhibit. So this is called the so-called G plus E problem. So G for genomics, E for the environment. And what you're measuring is the trait, and this process is called phenotyping. If you can do this in a scalable and low-cost way, then you can breed better plants because you'll have access to data that will help you figure out which genes matter the most to you. So currently, our robots are helping with the phenotyping. So what they do is they go through rows of corn, trying to measure different traits of the plants, and then provide this information to the breeders so that they can put that into their pipelines and breed better seeds. The next step would be to take these robots into existing agricultural fields where they'll essentially act as monitoring systems. Now, the key benefit they'll have there is that they'll be under the canopy, right? So they'll be up close, very close to the plants and the roots, and they'll be able to see the plants from underneath. This is different than what drones can do. Drones can fly from over. They can collect a lot of data very quickly, but that data does not have the level of resolution that you can get from under the canopy. And also, there's data that's hidden under the canopy that's simply just not observable by the drones. So this data will then be useful for detecting diseases and nutrient deficiencies much earlier than it would be possible to do that with drones or satellites. Then the next step would be to add capabilities to these robots to do some kind of manipulation in the environment, such as weeding or pruning or something simple. And then finally, we get to a situation where we now have small robots that can do interesting things in difficult environments. And this really allows us to rethink the way we do agriculture, right? So you mentioned these large equipment, these very large farms. So the reason we have the large equipment and the very large farms is because today farming can only be profitable if you do it over a very large scale. That's why in places like India or Africa or parts of Asia, farming is not very profitable because people own very small land and they have to employ a lot of labor to just take care of that small land. In the US, because the farms are big, because they can make a lot of money, they can afford the big equipment. And then the main problem is, how can a single person or a very small family of maybe 3 or 4 people can take care of very large farms, 2,500 acres or more. But if we can make robots that are small, low cost, and dexterous, then we can flip around the way we do farming. Instead of growing 80 acres of corn, we could grow small edible gardens which have multiple different plants together. And this would be a very different way and a fundamentally more sustainable way of feeding the globe than what we're doing right now.
Okay. I got a lot of questions around that. If you were to grow more than one type of plant, wouldn't that make it harder for robots to move amongst the plants because the plants are shaped differently and they're different widths and sizes? And it seems like if you knew that, a stalk of corn had the approximate same dimensions and spacing, it'd be easy to move amongst them versus, 4 different kinds of plants.
Yeah, absolutely. You're really pinpointing the research agenda there. So yes, it becomes a very difficult environment for the robots to operate, which is why our philosophy is small, low-cost hardware, but very intelligent software. So robotics is, one part of the robotics is the hardware, and the other part is the AI, or artificial intelligence, or some people call it autonomy. So we're working on both aspects. So we feel that the small hardware is enabling for this new type of scale-neutral farming. And in order to get there, though, we have to create these new types of artificial intelligence and autonomy algorithms that enable this small robot to operate in a much more complex environment. So in a way, we are trading off girth and power and size with intelligence. Does that make sense?
Well, yeah, it does. And in a small farm, too, every plant is important. So I can see in a gigantic, 1,000 acres of corn, you can treat the field in a bulk way with pesticides or whatever you need, and it's fine. You'll get most of it in the collection. But if it's small and there's only a few of each type of plant, each plant you got to watch out for, otherwise you're in trouble. So I'm picturing the machine vision, like a little, tiny little vehicle, driving amongst the plants and looking at them. And this one, it sees spider bites on it, so it can note that and you can do a treatment. And this one is turning yellow and wilting. And that one, it's a lack of nutrients. It can inject some nutrients. And, I can see how it would customize the treatment of the plants and let you know with each one what's going on.
Right. It's like your own little gardener, right? And that's what you would do if you were growing a little garden in your backyard. Now, that doesn't scale very much because of the intensity of the labor, like all of this specialized care that you have to give. So we're hoping that these types of robots will make that scalable. Now, there's many benefits of growing these gardens. There's a whole science behind it. It's called the science of polyculture as a production system. And I have colleagues here at the university, Sarah Lovell Evan DeLucia, and several other people who are exploring these types of systems. And the benefits of doing this is that the plants can help each other out, right? So some plants can maybe fix nitrogen, others can use that. Some are taller, others are shorter. So if we can get robotic systems that can maintain this large heterogeneous environment, then fundamentally we can build more sustainable and more higher yielding crops.
Have you deployed these little robots into some sample gardens, that are polycultural, and have you seen behaviors or things going on that you didn't see before? Because now you're wandering amidst the plants, continuously and watching them.
Yeah, that's a very good question. So, like I said, so we have a pathway towards this dream of polycultures, right? So currently what we're doing is we're deploying the robots in today's agricultural fields. So our robots, we had 30 of them out last year across the country and a couple outside of the country too. And they were running through fields of sorghum and maize and collecting data in a semi-autonomous manner. And so that's kind of where we think the technology is really ready to be kind of taken out, and we can have an immediate impact. And then we just started a couple of different projects in which now we're having these robots go through more complex environments. So we're in very early stage of collecting that data, but you're right. I mean, we're seeing these different types of challenges when we operate in environments that don't have the same level of structure that a row crop field would have.
Well, even in structured environments or non-structured, what are you seeing? What's interesting to you or surprising that you're seeing?
So one of the biggest challenges with field autonomy is change, right? So autonomous cars, for example, leverage a lot of structure in the environment. So what they do is they know where landmarks are. They know that they have where the roads are. They have somewhat of a good understanding of their environment that's mapped out over and over and over again, and they can refer back to that to make sure that they are in a specific part of their path. But when you go into the field, every day the field looks different to the sensors that are on the robot. So there is this challenge of how do you handle this level of change and uncertainty over time, right? So for example, if it rains, suddenly now the paths that you used to use are no longer accessible to you. So the robot has to have a higher level of understanding of the environment. So this has been, I think from a research standpoint, how do you enable this robust autonomy algorithms? That's a big challenge. And one of the ways you can do that is by enabling the robot to learn over time, right? So as it explores different types of environment, every time it goes through it starts to learn, okay, well, this is what I should do, or this is what, my supervisor told me to do in this environment. So maybe they are related. But then the challenge is how do you make this learning robust, and how do you understand whether the robots actually learn something that in a way that when you put it in a different environment, it's going to behave in a more predictable way.
Also, too, when I think of robots, I think of, little machines that move. But can a robot just be like an irrigation system that just sits there? Or is a robot, have to be like a moving thing, a moving machine?
Yeah, I mean, robots is a very general term, right? It's a term that's kind of more appropriate for all kinds of systems that close the loop between sensing and actuation is cyber physical systems, right? And this is a term that the National Science Foundation uses. And the idea is that these systems live in a physical world, but have a cyber component attached to them, right? So an irrigation system would be a cyber physical system, right? Now, an irrigation system could be a center pivot one, which is essentially a centralized system that just rotates, or it could be a distributed set of nozzles and valves and irrigation points. Now, while the first one is more like a traditional robotic thing where there's only a single kind of a system that operates in a predictable way, the other is distributed, and that comes with its own benefits and disadvantages. So the kinds of robots that we're talking about are actually even beyond these two types of systems, because not only are they moving, and their dynamics are part of the whole complexity of the system, but they're also distributed, right? So it's really a cyber physical system consisting of nodes that can sense the environment, act upon that information, and then position themselves in a way to optimally leverage their environment.
Yeah, because if you said that, you want to deploy a whole bunch of sensors over a field, that would give me one picture. But, deploying a whole bunch of robots is a completely different picture. That's why I asked. I guess, the devices cross the line between the two or incorporate both sometimes.
Exactly. So the big challenge in operating in large fields with teams of robots is how do you predict in places where you aren't there, right? So a brute force solution is, okay, I'll put thousands of sensors across my field, right? And this is expensive. It might be actually not really practical because, who knows which ones are working, which ones aren't. And it might not even be possible to actually embed the level of sensing into these thousands of very simple sensors. So what you might want to do is put some of them on the robots, and then the robots are kind of scouting this field. Now, as the robots go through this field, they can only see where they are and maybe a little bit around them. So really the big cyber physical systems challenge or the big AI challenge is how do you predict what's happening in the rest of the field based on the limited information that these robots are getting? And then how do these robots determine what paths to take so that prediction is improved?
Okay. Yeah, it seems like you may need an AI system that's trained on each type of plant. In order, what I'm picturing is the robots you're using or creating, they need machine vision to navigate their way. Then they need another kind of machine vision when they're looking at, maize versus sorghum versus some other plants to identify important features on each type of plant. It seems like they would need many different trainings in order to navigate a polycultural field, or even just one field. They need at least two kinds, it looks like.
Yeah. So that's a very good point. And that a lot of that comes back to the limitations of the existing learning algorithms, right? So we are very good today when we have large supervised learning data sets, so large labeled data sets. So if you gave me a data set which was like, here's a maize plant and here's different types, parts of the maize plant, here is a soybean plant, here is a nut tree and all of that. And then if I went through a standard machine learning system, I can train a particular neural network or other system to basically predict based on those labels, right? So if we went down that path, then you're right. We would need a very large data set with everything labeled. So what we're trying to do as one of those as research objectives is to flip this around. We're saying that, okay, a farmer, right? If they know one plant, they have a better understanding of some other plant. So how can we use these large data sets that we have in a more unsupervised manner to let our AI algorithms understand what a plant is, right? And then in the feature space of the plant, they can differentiate between maize and sorghum and soybean and maybe a palm tree. So this collectiveness, this compounding of understanding of the environment is really, we think, key to solving the agricultural AI problem. And that's again somewhere where these large teams of robots can help because they can go and collect this data in a seamless and low cost manner.
Well, it seems like if a little AI robot had a library of different AIs, like it would use one again to navigate between the stalks of corn so it doesn't run into them. And then it would use another one to orient itself when it's looking at a particular stalk of corn and say, okay, I'm at a right angle where I can see stuff. And then it would switch to another one where it says, all right, I'm looking at the corn. Let me look for spider mites or wilting or yellowing or whatever, So it's like, I could see that, again, if it just had a library of different AIs it could call upon at the right moments, that would work fine in the body of one machine.
Right. So it's a confluence of all of these behaviors, these intelligent behaviors, right? So like in our current phenotyping project, the ARPA Terra project, what we're doing is we're relying on the LiDAR to tell the robot where it is with respect to the stalks of the row crop, right? And these are breeding plots. So they go for about 3 meters, and then there is a skip row, and then there's another 3 meters of plants. And then, so as a robot, so one of the robot systems is making sure that it kind of stays in the middle of this plot and navigates, while other systems on the robot are getting the data that they need and processing that data. So this is a good case where this kind of decoupling is possible and can be done. But you're right. In other cases where manipulation is required, this kind of decoupling becomes harder. So that's why I mentioned closing the loop between actuation and sensing is really the key in a polyculture environment, because you may only be able to reach a part of the plant if you position yourself in a particular way, right? But if you position yourself in that particular way, maybe some part of the plant is no longer visible to you because of the way your sensors are configured. So really the robot needs to have an understanding of what it doesn't see. And in classical controls literature, these types of problems are referred to as observability problems, where how can you reconstruct the full state of the environment by using only a few measurements from the environment. And really, this observability or perception is at the is the key and the most fundamental problem in field robotics. If we have good perception, a good understanding of the environment, good models that enable the robot to plan and do control, even when only parts of the environments are visible, then we can approach autonomy and manipulation.
Well, I think actually, now that I think about it, you got a very tough problem, because if you picture a bunch of discrete plants that don't touch each other, that's one thing. But if they all start growing, I've seen, grow houses and stuff like that, and the plants grow over each other and they intermingle, and you've got some plants that kind of take over. I mean, how would you ever distinguish plants that are growing and forming a canopy, and they're leaves are in front of those leaves, and these are, they all get jumbled together. It seems like that'll be super difficult.
Right. And that's very true. So one of the things that happens is that if you say, just take a snapshot, right, just one image, and I show it to even experienced humans, sometimes it's very difficult for them to tell what's going on. So the way humans seem to deal with this and other animals is through motion, right? Is through sequence of images. So they move around. Sometimes they even manipulate, like a human would go and pick something up or move it around. And this information, this sequence of information helps the person to better understand the environment, right? So going forward, that capability is very important in the robots to be able to synthesize sequence of information. So it's both spatial and temporal to deal with this complex environment. And another thing I'll mention here also is, there's been a lot of work on robotic apple pickers, berry pickers, grape pickers, and all types of things. And, there's some very interesting work that has been in the lab setting, but it has never really made it to, out into the wild, even though there is a massive labor shortage in agriculture. And what people have been doing mostly is they're taking these industrial robots, these large, robots that are metal built with electric actuators that are really good at doing precise tasks really rapidly. And they're hoping to take them into the fields and hoping that they'll be able to deal with the very unstructured environment that's there in the field. Whereas these robots can do very precise tasks very rapidly in a very structured and clutter-free environment. So one of the things that we're working on now, and we're just starting a project with the National Science Foundation on thinking about different types of manipulators that aren't maybe hard and therefore precise, but soft and therefore more dexterous and more supple, and they can get to difficult parts. Maybe they can't pick 1,000 apples in an hour, but they'll be, if you had a large team of them, these soft-armed robots could go through and day and night just keep picking and doing tasks in the field in a fundamentally more simpler way than hard arms would be able to do. Do you want me to elaborate that a little bit more?
Yeah, well, it brings to mind two things. I mean, one thing, to refer back earlier, this is just in my idea, is I could see what might be necessary is you would go through a field in the early stages when you have seedlings or seeds and you register each site where a plant's going to grow. And then you do that over time. As the plants grow in, you're registering, okay, here's this plant, we've located it, oh, here it is again. And you kind of do a time lapse and see how the plants start growing. So then when it gets to the canopy part and they're all grown together, you're much more likely to know, okay, this is where this plant's location is registered. We still know it's this type of sorghum, but now we can look at it and kind of understand how it's interacting with its neighbors because we already know its history and where it's come from. And we can kind of time lapse the way it looked and figure out what it looks like now versus a couple of days ago when we looked at it, or a month ago. That's one thing I thought of.
Right.
Oh yeah, and then the other thing with the pickers, this is another subject. I imagine a bunch of like snake-like appendages that can touch different parts of the plant and come together or not come together, and it's like a hand with super long fingers, and the appendages again are like snakes, and they can twist and move and form and deform and grab things and hold branches and pull them and push them, that kind of stuff. So those are the two things that came to mind as you were talking.
Right, like octopus arms, right?
Exactly.
These octopus arm type things would be on the robot, and they can reach very different parts of the plants in a very unique way. You can wrap around, you can reach through foliage, so you can even have sensors on the tips of these arms, and using those sensors, the arms can see and reach parts that the sensors on the robots won't be able to detect.
I'm just thinking, you've got a lot of work ahead of you. This stuff seems really complicated.
Absolutely. Yeah, this is
cool. It seems really cool, but complicated.
Yeah, it's complex. It's very challenging, and it's something that takes some time to appreciate, right? I really think that agricultural autonomy, AI and robotics will really open the next frontier for AI and decision making, because it's one of those things where we've kind of tried to solve agriculture by looking at it from this industrial perspective, right? We've said, okay, we'll just grow over large acreage, the same type of plants, and then we'll make sure that the seeds are such that they're resistant to the herbicide, so we can just go and spray and pray, right? And now this is clearly something that has helped us to date. We have definitely solved food security problems in certain parts of the globe, not everywhere, but certainly there is this method does create sufficient food. But as we look into the future, as the population grows and as we need to be more careful of the environment that we live in, we need to think about different ways of doing agriculture, ways that are essentially more centered towards specific dexterous care that our ancestors were able to provide because they weren't doing anything else. They weren't, they weren't writing code for Google and Facebook and building large dams and bridges. All they were doing was agriculture. So they could dedicate that level of labor to agriculture. Now that we've kind of resolved food security in certain parts of the globe, many people are free to do other things. But what we now need to do is bring that technology that we have developed back into agriculture to lead us into a next generation of agriculture, which is characterized by dexterous equipment that can really take care of each plant on its own level and of different plants that are interacting with each other in a heterogeneous environment. And this is not, like you mentioned, it's not an easy path to get there. But as we go towards that path, we'll tackle and solve many challenging problems in AI, machine learning, control, robotics, and this will certainly lead to good things, not only in agriculture, but in other spaces.
Gotcha.
So one of the things that I always like to think of. So I'm by training an aerospace engineer. So all of my degrees and everything have been in that field. And what I really like about aerospace is that aerospace really created these very complex systems and made them work reliably over ridiculous periods of time. So airplanes, these are like impossibly complex systems that we couldn't even imagine 100 and something years ago. Today have less accident rate than crossing the road. Now, The next challenge is to get that level of reliability and engineering in extremely complex systems like agriculture, right? So I feel just as how making airplanes and launching satellites led to other technologies like GPS and even ballpoint pens, I expect that pushing agriculture to the next level will lead to other technologies that'll make our life easier and better.
Well, very good. So last two questions. So where are you at in your development, and what's ahead for the next year or so in your development plan?
So we're walking this path that I mentioned to you before, starting with phenotyping, focusing on high quality data, then going into monitoring, then field scale manipulation, and then finally into polycultures. So right now we're at the phenotyping stage. We've made the robots at the university. We've deployed them throughout the U.S. and a couple of other places in the world through a startup that we formed. It's called EarthSense, and this startup is now really working with users to take the technology from the university, de-risk it, and deploy it widely. So as the phenotyping technology gets deployed, we'll be getting more information and data on how to do the field scale manipulation like weeding. So we have a couple of projects in that area now from federally funded, in which we're exploring how we can do herbicide resistant weeding and design of soft arms. Then once this is kind of in the next 3 years, this is what we're going to be working on, and then we'll see where it goes from there.
Okay. Yeah. All right. Very good. So what's the best way for interested parties to get in touch with you?
So I think the best way is to write email. My email is girishc@illinois.edu. You can also go look up our website. It's daslab.illinois.edu, or you can just search my name, and I think it probably pops out.
Well, that's great, Girish. I really appreciate you coming, and it's really interesting stuff you're working on. I think it's very cool.
Thank you very much.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.